All right, we're going to revisit a tension problem. I'm going to have one like this on the test tomorrow, I think. I think I'm feeling this one. This is a pulley and blocks. Yes, sir, Mr. Ryan, we're going to revisit the pulley and blocks question. One pulley. Tied together with a massless rope. Strung over a massless resistance-free pulley, Riley. All right. This is block B. It's 3.0 kilograms. This is A, 2.0 kilograms. Okay. All righty. Now remember, Christian Leitner, when we have a pulley problem, we treat it as a tug of war. Let's take a review here of what we got. We got gravity pulling it this way. That's pulling that block down this way, right? And gravity's pulling that block this way, right? And there's going to be a net acceleration of the two, right? Which one of these things do you think is going to win? Yeah. So the net acceleration is going to be, it's going to be down this way. Okay, see that? Now, once you take the string, all right, take it off the pulley and make it a tug of war. Okay? Make it a tug of war. There we go. Okay, so this was block B. This was 3.0 kilograms. This was block A. This is 2.0 kilograms. So now we've turned it into a tug of war. Which way should our gravity arrows be pointing? Out. So you got gravity pulling it this way, and we can make that negative, and we can make this positive gravity, and we'll have a net acceleration that way, right? All right. Now, we also, Ryan, have to take inventory of where all the pulling that's going on, right? So we have gravity of block A pulling that way, gravity of block B pulling that way. We have a net acceleration. Well, which ones are moving with net acceleration? One block or both blocks? Both blocks. So the tension in the rope is caused by block B pulling, a net acceleration of block B going this way, and A is also going which way? This way too, at the same net acceleration. So look how many arrows we drew. We drew 1, 2, 3, 4. All those arrows are going to result in tension on the rope. Because think about it, Ryan, block B is pulling on the rope this way, right? And block A is pulling on the rope that way, right? So they're stretching the rope. Okay. What we're going to do is we're going to part B, acceleration of the blocks first. Sorry. Okay. Here we go. Gravity times 2.0 kilograms. What's that? You guys calculate. Negative 19.6. So you got negative 19.6 newtons this way. 3.0 kilograms times gravity. 29.4. Good, Chris. Christopher. Well, that's good. Now that's just from gravity. Okay. So we need to find a net acceleration. Alrighty. So we're going to do part B first. So net force. Force net. Well, what's that the sum of? Yeah, all the forces. You got block A, you got block B. Okay. So if block A is pulling with negative 19.6 newtons and block B is 29.4 newtons, right? Well, then that equals how many newtons? Net. Okay, now that equals 9.8 newtons. Now, what is moving, Miss Allie, with that net force? Both blocks, aren't they? Well, isn't net force the same thing as mass times acceleration? Okay, well, it's both blocks then. It's both masses. If both of them, Christian, if we have a net force, that means both blocks, doesn't it? So net force due to gravity. So that means if you put the two masses together, Greenie, 2 kilograms plus 3 kilograms, you'll have 5 kilograms. You need to tell me the net acceleration going on, please. What is the net acceleration going on, please? 1.96 meters per second. Okay, we've done part B. Now we're going to find the tension on the rope. Now that's the net acceleration. That's where they're accelerating. Both blocks moving this way. Ryan, are you all right, man? 2 days in a row, you've looked sick. Well, he might be sick. But look, now we got to find the tension. Even though they're both moving that way, is 2 kilogram block still pulling on the rope this way? It is. So we've got this, we got that, and we also have 2 kilogram block moving at 1.96, and we have the 3 kilogram block moving at 1.96. So if we want to find tension, okay, we have negative 19.6 newtons plus 29.4 newtons. And then this 2 kilogram block is also moving at 1.96 meters per second, right? Meters per second squared. So that's the 2 kilogram block moving at 1.96 meters per second squared, and the 3 kilogram block moving at 1.96 meters per second squared. So we had gravity, gravity, net acceleration, net acceleration. Put that all together, and that is the tension that the rope is experiencing. So look, Alejandro, gravity's pulling this block that way. It's also net accelerating that way. That block right there is accelerating that way. But this block is also pulling back on the rope, and it's stretching it, isn't it? Can you picture that in your mind? Stretching the rope? Even though they're both moving that way, the weight here is still stretching it. Add all that up, please. Negative 19.6, 29.4, 2 times 1.96 plus 3 times 1.96. And you guys should get like what? Close to 20? 20-ish? All right. So 19.6 newtons is the tension on the rope. Make sense? You satisfied with that answer, Ryan? Riley, are you satisfied? Chris Parham, are you satisfied with that answer? Greeny, are you satisfied with that answer? Hey, look at that. He's got a calculator, not a video games. James, you satisfied with that concept, with that answer? Okay, folks. So I just wanted to revisit that. So even though they're both moving this way, you still have a stretching of the rope caused by this. Yes, sir, Terrence. You can choose whichever direction is positive or negative if you're on a pulley, man. Okay. You can say that, hey, this one's the negative one and this one's the positive one. Yeah, plus and minus really just mean opposite directions. Okay, absolute value, yeah. All right. And then, guys, the other problem I wanted to do real quick was there's going to be a centripetal force problem on it tomorrow. So go to problem number 110 about the skater. Quite possibly. How many problems, hon? Probably 7,000 problems. Ariana, what did I say about these problems that I assign? Why are they important? Why should you take a look at them? Oh, well, then I guess you probably should. Okay, the next problem I want to do. Right here, number 110, okay? I'm going to copy that. Tools. Camera. Area snapshot. No. No. Dangummit. Let he wants to take a knee, man. He's good. When he takes a knee, he feels like he's accomplished something. So he's accomplished in making you nervous. Good. All right, dudes, here we go. Let's do this problem. Or let's copy and paste it. Let's do that. Kilogram speed skater. Here we go. Draw a speed skater. Here we go. Speed skater. What do you think? With a helmet? Okay. Mass is 60 kilograms. Already going with a velocity here of 18 meters per second. The radius of the turn is 20.0 meters. Obviously, that's a lopsided drawing. So you need to find out the frictional force between the skate and the ice. All righty. Is there a centripetal force pushing him in toward the circle? Yes. Is the centripetal force in this case equal to the frictional force? It has to be, or else he would slide. Okay? Well, what is the equation for centripetal force? Mass times what kind of acceleration? Centripetal, right, James? All right, so that equals frictional force. Well, how do you calculate centripetal acceleration, Ryan? That's exactly right. Velocity squared divided by r. So you have mass times your velocity squared divided by r is equal to your frictional force in order to get around this circle. Otherwise, he would just slide. Skates would come out from under him and no circle. Calculate. What'd you get, Desmos? No way. Way more than that. You got to square the velocity, divide by the radius, and multiply 972. You got it, man. 972 newtons. And you're probably thinking, Allie's thinking, my gosh, that's really heavy. Well, you know what? When you go around a turn, do you get heavier? You do. That's why it's difficult to run around a curve. It's more difficult than it is to run straight. Yeah, you change your direction by applying a radius, and therefore you feel heavier. I know, but you weigh more. It's harder. You feel like you're going faster because you're experiencing acceleration. Are you talking about the car or you? I'm talking about you running. Okay. So when you go around the curve of the track, you feel like you're going faster. I mean, I guess because you just see the ground. It's an optical thing. You just see the ground disappearing at a curve, and it looks like it's disappearing at a faster rate. But in actuality, when you're running like that, there's more. You know what? You don't pull your hamstrings as much because you're using different muscle groups to do that. So you don't overstrain one particular side of the muscle, but you are getting slightly heavier when you go around the turn of the track. You go around a tighter circle, it's even harder. It's even harder. These football players and soccer players definitely feel it. Okay? Like when they're chasing after the quarterback or the running back and they have to chase somebody, they have to bend and they have to move. That's hard to do. It's called change of direction. You've done it in soccer, right? Yeah. It's because you're physically getting heavier doing it. Basically. All right. So those could possibly be on there.